I'd like to extend a very warm welcome to Cornelia and her group from the parallel program. And of course, Stefaan, who's going to give the first of his talks.
Thank you very much. It's a great pleasure for me to be here in Cambridge and give this series of lectures, so thanks for the invitation. And the topic will be, very broadly speaking, about representation theory and cohomology and homology. And now here I could put many words, but let me stay for the moment with standard invariants. Now, what are standard invariants? I will be building quite a bit on the lecture series of Dave Vaes, who was explaining to you a lot of the theory of subfactors. So subfactors in the sense of one Johns. And whenever you see this inclusion n in m in any of my lectures, these will always be 2 unfactors. So inclusions of 2 unfactors of finite Jones index. So the Jones index being the n dimension of m will be assumed to be finite. So that's the kind of structure that has been looked at, introduced by von Jones, and that Dave discussed in great detail. And the whole point is that attached to this kind of structure, one can somehow see 2 different types of things. And very vaguely speaking, there is a kind of discrete invariant that comes in many flavors, and that I will explain. I will introduce it again. And the discrete invariant, it comes under many names and many flavors. The standard invariant, or it comes in the form of tensor categories, and then there are a few adjectives to be added. Rigid C-star tensor categories, or planar algebras in the sense of one Jones. That's yet another formalism. And I will come back to all of these. The whole point is that somehow you should think of this discrete invariant as a structure that generalizes countable groups. And countable groups will indeed be a proper sub-thing of this kind of structure that one looks at. And then actually a subfactor is not only its invariant, no, in a way it is also saying how the invariant acts on, well, M. Sometimes it will be more convenient to double M and look at M tensor product with its opposite algebra, as we will see. Now, why am I stressing this? Because there is a lot of attention in the theory of, say, planar algebras on classification of, say, these discrete invariants in the case where there are finitely many irreducible objects, if I stay in this language, or if I stay in the group theory language, it's on classification of finite groups, say, but then of finite planar algebras. So there has been a lot of attention and a lot of progress on that. But that's not entirely the same as classifying subfactors. It's classifying their invariants, because the second question is, how can these invariants act on 2 unfactors? And we will come to results of Sorin Popa saying that when you restrict to amenable invariants and amenable factors, then this is a complete invariant, and there is no distinguishing between the 2 questions. But anywhere else, there are a lot of open questions. We don't know which type of invariants can act on which type of factors. I mean, there are a lot of difficult problems there. Okay, now the main goal will be to discuss in these 4 lectures representation theory and cohomology for this kind of discrete structure. So this structure that I will have to introduce, so we will represent it on Hilbert spaces in the right way. And we will do cohomology cohomology, and in particular L2 cohomology, introduce L2 Betty numbers. And maybe another advertisement, I don't know whether there are many students around in the other parallel program, but in lecture 3, meaning on Thursday, I would start with a basically self-contained introduction to L2 Betty numbers, first for groups, and then gradually for these more general structures, so that might be useful for them too. Okay, so maybe I have to come back on the different points of view on the invariant. So on the standard invariant of a subfactor. So the standard invariant of a subfactor can be viewed in several different ways. And the first way, the initial one, started with Jones' basic construction and the so-called Jones tower that Dave explained to you yesterday, namely, with the inclusion of finite index, actually for free comes a whole tower of 2 factors. And as you may remember, these new 2 factors m1, m2, and so on, they're each time generated by m and a projection, the so-called Jones projection. And each time you get an inclusion of the same index. So the whole point is that somehow on the L2 level, the orthogonal projection of m onto n is a projection that you add to the algebra, and that creates a new algebra m1. And then this inclusion is an inclusion of 2 factors with the same index, so that you can iterate the construction, and there comes out this tower. Now this tower has then the property that all so-called relative commutants are finite dimensional C-star or von Neumann algebras. That doesn't matter then. So I say Bij. When I look at all operators in Mj that commute with Mi, what I get is a grid, 2 parameters, I and j, is a grid of multi-matrix algebras, because it's a finite dimensional von Neumann algebra, direct sum of matrix algebras. But not just abstractly multi-matrix algebras, they are sitting inside each other in all kind of obvious ways, and they contain the Jones projections that also satisfy all kind of relations. They contain the Jones projections because at each stage there is a projection added, and to get... Okay, even if you don't know what all this is, it's not a real problem. What you have to keep in mind is that attached to the inclusion of 2 factors is a grid, 2-dimensional, of finite dimensional algebras with a system of projections sitting inside, and this kind of structure has been axiomatized. So that is, there is an axiomatization due to Popa, and then it's called a lambda-lattice, and the number lambda would be the inverse of the index. That's just a convention. So Popa calls that a lambda-lattice. It's a quite complicated, I would say, combinatorial structure, because the point is to have this whole system of multi-matrix algebras with all their kind of inclusions and their projections and all kind of relations. Yeah? So that's a complicated structure. Now there is another way to view the same data, and that's more categorical in nature, although it's, if that word exists, I would call it concrete category theory. So what's the concrete point of view? Well, the point is that you start with M, or if you prefer L2 of M, it's Hilbert space completion, that doesn't matter too much. You view M as an NM bimodule to encode the inclusion. And then, as Dave explained, you can make all kinds of tensor products. I think I have to put this down. Here it's going. Ah, that's what I expected as next, that the light will go on. So how to keep and the light on, and that I still don't know, actually. Well, there needs to be a blackboard up there to have the light on. So starting with an NM bimodule, you can now make a whole bunch of bimodules. So we make tensor products. Now, tensor products relative over n. Okay, you can do that a number of times, and that's not just, there is a very clear link with the Jones tower. So link with A is that if I view this M1 as an MM bimodule, in this, so the M1 of Jones is the same as this as an MM bimodule. So not only this, if you think a bit further of, so this is just an example, so this is one link. Another thing that you may look at, for instance, is that what are the endomorphisms? The n endomorphisms of n. If you follow all these identifications, it will turn out that this is precisely the operators in M1 that commute with n, if you do all things right. So what do you see appear? What you see appear is that these higher relative commutants that were the invariant over there are now nothing else than endomorphisms of bimodules. And therefore, from there comes the other point of view, where you would say the invariant is something else. The standard invariant is now no longer the lattice of relative commutants, so other point of view on the invariant. It is the so-called two-category of all. And now there are four types of bimodules that can appear: NN, MM, MN, and MM. Bimodules appearing in these tensor powers. So you take all these tensor powers as many times as you like over there, which you can view as an MM bimodule, but does also as NM and in all possible ways. And now you see that there are obvious tensor products that you can make. So there is a natural structure of a two-category, actually a rigid C-star tensor two-category. There is duality, there is all kind of nice structure as you wish. It's not just the two-category, it's a two-category plus its generator. Namely, there is a favorite NM bimodule, namely M. And you can formalize this if you really write down proper definitions, then a lambda lattice is exactly the same as a rigid C-star two-category with a generator. Okay. Then there is a third point of view, and that's planar algebras, that I won't use so much. And planar algebras is a way to, it's a diagrammatic, a very efficient diagrammatic way to write intertwiners between tensor products of objects in a tensor category, in a way. That's one way to phrase it. It's a very efficient diagrammatic language to make computations with intertwiners, and therefore it's a diagrammatic way to write these endomorphisms isomorphism spaces. Let me now stay with MM, for instance. And I won't make any drawings. I will not use this approach, but for instance, I mean, if you have seen drawings like this. I mean, if you have two outside things like this and here, you could make a drawing like this, for instance, and that would be which type of intertwiner? Well, we have a tensor product of 2 and a tensor product of 2, and this would be the combination of the, or the composition of the canonical duality intertwiner. Here it would be the product map, it's adjoint, and there are ways to represent canonical intertwiners and so on and so forth. I will not go further into that picture. Okay, let me reassure you, I will give more precise and concrete definitions when we get a bit further. So the whole point is that there are 3 different points of view on the standard invariant of a subfactor. And what we would like to understand is how to define this precisely, and then how to do some harmonic analysis for these structures. Okay. Now, why? Why trying to do some harmonic analysis and say, inspired by representation theory for groups, results for these standard invariants? But I would say that the main motivation is Popa's classification theorem from 1992. Saying that the standard invariant is a complete invariant when n and m are the hyperfinite to one factor, so that's the first amenability assumption, and the standard invariant itself is invariant, is amenable. So there is a notion of amenability for this discrete structure. That one you can define with more ad hoc means. At a certain point we will come to the graph that's associated, the weighted graph associated to the subfactor, and then it will be a very natural amenability or absence of spectral gap property for that weighted graph. So you can formulate that quite intrinsically. So under that amenability assumption, and when this factor itself is amenable, then Popa proved that the standard invariant is a complete invariant for the subfactor. So motivated by this, it's quite natural to define and see what happens, things like property T, Haagerup property, and other representation theoretic type of properties for groups, and try to define them for standard invariants of subfactors and see how they relate to subfactors themselves. Now that's actually what Sorin indeed did. So that was done by Popa. And I will explain how. Through the symmetric enveloping inclusion. And I will spend some time in the second part of today's lecture introducing this structure. Through the symmetric enveloping inclusion, P in S, that I will explain in detail, the whole point now is just the following. Associated to the subfactor inclusion, he built a new inclusion of infinite index. It's of a very different nature. And then the advantage was that a lot of the existing theory on property T, on amenability, on the Haagerup property, a lot of the existing theory for two factors could just be used to say, we define these properties by saying that the inclusion should have these properties that were known, yeah? And then could be studied. Now this had another disadvantage. The disadvantage is, of course, that the construction of this new inclusion that I will present in a minute, this construction depends not only on the standard invariant, it depends on the subfactor. So for each of these individual properties, every time there was a separate proof saying that, okay, if you realize the same standard invariant with two subfactors, then also the properties pass from the one to the other, and each time you have to prove this. So it's clear that this is not the right approach in a way. You want to define these properties intrinsically for, say, tensor categories or for lambda-lattices and so on. And for lambda-lattices, that's exactly what Sorin and I did in 2014. Now, the point is that at the end of 2014 and then throughout 2015, a lot happened at the same time. So let me try to make a little scheme and then say how I will present things this week. The point is that so at the end of 2014, what Sorin and I did was to give an intrinsic definition say of what? For, say, lambda-lattices, tensor categories, of property T, the Haagerup property, amenability that was already done, but also of what is a unitary representation. And then things gradually and actually quite quickly got understood much better, because then in January 2015 there was already another paper by Leuven Yamashita, focusing completely on the categorical part, so starting with the tensor category and reinterpreting things as unitary representations being is the same as so-called unitary half-braiding, not for the category, that would be too small, for an extension of the category allowing for infinite direct sums. So that's those who have heard the word. I mean, it's the Drinfeld double, the Drinfeld center, I mean, the Drinfeld center of the int category. So that's a purely categorical approach to what is a unitary representation. And then 1 month later, the picture was completed. And that is actually connected to Jones-Reznikov as well. We'll say in a minute. One Jones, because here there will be another Jones. Corey Jones. Who could clarify that a unitary representation is the same as an ordinary representation of another new concept, the tube algebra. Okay, I know this means basically nothing to most of you, I guess. The only point I want to make is that on a very short amount of time, the whole picture got clarified and then was even further generalized by Popa, Shlyakhtenko and myself. And what I will try to do now is to take a much more systematic approach and give really definitions and concepts. And it will, of course, come from a mixture of all these insights, and I will not anymore every time try to say where things came from. Yeah, there was a whole kind of movement going on. Okay, so now we start from scratch again, only assuming a subfactor. So let's now be a bit more specific. And so that's the first approach using the symmetric untitled inclusion. Yes, inclusion. Still puzzled with the language. Continuous fact. Yeah, I can't help it. I will keep it like this because of the writing. So the starting point is just to find the next subfactor, and then Popa did something very interesting. Namely, there is a new inclusion of two unfactors, where T is nothing else than doubling M, tensoring it with its opposite algebra, and then he builds a new algebra S. This is obviously to Popa. A new algebra S with the following universal property, characterized by, so is the unique two unfactor generated by T, by n tensor M opposite, and a single projection one single projection E, and the following relations, there are two relations, such that, first of all, M and E are the basic construction of Jones for the inclusion of n in M, and maybe I should write M tensor 1 to be very clear. Because I have a copy of M sitting in my algebra, and I require that this extra projection plays the role of the Jones projection for the inclusion of n in M. In particular, if I put the projection E around an element from M, its projection onto N. Yeah? But at the same time, it plays the role of the Jones projection for one tensor M opposite. Then for n opposite in M opposite. So at the same time, within the same algebra, we realize the basic construction for n in M and for n opposite in M opposite. Now, the fact that this exists and that this is unique, it's a non-trivial theorem, and even to analyze the whole structure of this algebra is a priori not so clear at all. For instance, it automatically contains the whole Jones tower. So automatically the entire Jones tower sits inside the algebra S. And you can actually even say how it sits with respect to the other copy, because the Jones tower, if I take the convention that now this is M0 and this is M-1, there is not only the Jones tower, there is also a possibility to choose the so-called tunnel. Okay, so if you not only look at M having a tower, but also having this nested subalgebras given by the Jones tunnel construction, then you can actually say how Mn sits inside S. Then Mn is nothing else than, so now I should do things write as the relative commutant of minus n. So it's a quite remarkable construction, because minus n sits inside m, yeah, it's a tunnel construction. So I can look at which operators in S, which elements of S will commute with m minus n in this part. Of course, in particular m, but much more. And indeed, what commutes with it is exactly the nth part of the tower. Okay, now if you want to prove theorems and do constructions with this point of view on the SE inclusion, it's very, very hard. And indeed, there was another point of view introduced shortly after that by Longo and Reren. So the Longo-Reren point of view. And Longo and Reren did it in the case where you have only finitely many irreducibles, so finite depth case. So I think the general case is due to Masuda. And that's a construction, a more, well, not such a unique characterization, but the real construction of S. So let me show you how this construction goes. So we start with the one factor inclusion, and I will tell you how to construct this new von Neumann algebra S. Well, the construction goes as follows. So denoted by C is the category of all finite index n bimodules appearing somewhere in the tower, yeah? So that's why I'm saying that I will never do more than this type of concrete category theory. Whenever I pronounce the word C-star tensor category, what I really mean is that you just start from a subfactor and you look at all the n bimodules that appear somewhere in such an iterated tensor product, and then it's clear that this family, if you wish, of bimodules is closed under taking tensor products by construction, that is closed under taking adjoints, and that you have all structure you wish. And this structure, of course, you can take abstraction of the fact that it came out like this, but anyway. Okay. So denote by C all n bimodules that appear in the Jones tower. So I can look at the irreducibles. So every irreducible is realized irreducible is now realized by an m bimodule that we denote like this, say H alpha. It's a subbimodule of some tensor power, and I take each only once. That's what I want to say. And now I can define a dense star subalgebra of S. So define S mod as just the direct sum algebraically over all irreducibles of what? Of the following vector space, H alpha tensor H alpha bar, where I view this one as an M tensor M opposite bimodule. Indeed, H alpha is an MM bimodule, and then quite naturally H alpha bar is an M opposite bimodule. So the tensor product is an M tensor M opposite bimodule, and if you want to be very strict, you would only take the so-called bounded vectors, but let's not go too much into these details. So this is just a vector space. Now there is a product. First of all, of course, it does contain M tensor M opposite, because M tensor M opposite is the place where I take the trivial bimodule. Yeah. So the trivial object in my category, the trivial bimodule is M itself. So M itself is the trivial bimodule, and so M tensor M opposite I have from the start built in. Okay. Now, what is the product? Maybe I have to introduce, well, no. Here is the product law. So assume that I take psi1 and psi2 in H alpha. And mu1, mu2 in H beta. So you may guess which kind of terms that will appear in the product. Of course, all bimodules that appear in alpha H alpha tensor H beta, yeah, that should somehow contribute. And indeed, the definition is that you take the sum, because it's with components, of all gammas, all irreducible bimodules. There are only finitely many of them that appear in H alpha tensor H beta, and then I have to write vectors, really vectors in the bimodule, and I sum over an orthonormal basis of isometries x in alpha, beta, gamma. And I think the category theorists won't like my convention. For me, this is a map from gamma to alpha tensor beta. That's bad, no? Should I try to do it the other way around? But then I think I have to try to do it the other way around. I will do it the other way around, but then there are no guarantees. You know, I mean, maybe we should have a discussion over some coffee at a certain point, because I think I'm right with the convention, because if you compose things, you should compose them like this, no? I prefer to compose things like this. And you prefer to compose things. Anyway, it's because we somehow write in the wrong direction, but yeah. So here comes the sum. So alpha tensor beta it's a bimodule. It decomposes into a number of irreducibles. Each irreducible can appear with a certain multiplicity. That number of isometries you will need to fill alpha tensor beta. And now comes the clue. So x goes from gamma to alpha tensor beta. With x star I can come back. And that's the formula. Now, it's exactly because of this balancing here and there that the choice of the orthonormal basis doesn't matter. And that's why it's so crucial to have H gamma bar, and so on. And then you can check out that this is an associative operation. You can define the star operation, and you can define a weight.
So you say the number of irreducibles doesn't have to be finite here, you said this works.
But that will automatically be true. I mean, we have finite index bimodules. So a tensor product of two finite index bimodules is finite index.
Right, but you're not assuming the total number of irreducibles is finite for this construction.
No. In the construction, no. But in the sum here, everything is finite.
Yeah.
So there is also an adjoint. It's a star. And there is a weight, a functional. A quite natural functional that's just picking out the component with epsilon. So let me say tau of it would be 0 if alpha is not the trivial bimodual, and otherwise the usual trace on M tensor M opposite, which is the part where alpha is the trivial bimodual. And that was just sitting inside here. And so this is a positive functional. Positive functional on S0. It has a, actually you can compute, it has a nice modular automorphism group. You can nicely complete into it's a state. You can nicely complete into a von Neumann algebra inclusion. T inside S. Now I was stressing modular theory, indeed, that there is not, maybe not a trace. The whole point is that we get a trace. Tau is a trace precisely in the so-called extremal case. Now, if you don't know what this means, usually this is a standing assumption when you work with subfactors and planar algebras. This is equivalent with saying that the bimodules that appear in my story, all bimodules in C, all those generated by tensor powers of M itself, all bimodules in C have equal left and right dimension. And in that case, we really get an inclusion of two unfactors. So the whole point is that, so Dave explained you dimension theory of bimodules. What is the index of a bimodule? So whenever I have an MM bimodule, it has a left dimension, it has a right dimension, and somehow in the irreducible case, its true dimension is the square root of the product of those two, as Roberto Longo defined. There is a kind of non-unimodularity phenomena when left and right dimension differ, and then the fraction between the two goes into the modular data of this state on S. Okay, let's continue with the extremal or unimodular case. Okay, so what is all this? So let's try to recapitulate, and then you can even forget a bit of this whole construction. The whole point is that starting with a finite index subfactor, we build a new inclusion of T in S, and if in our category there are infinitely many irreducibles, so in the non-finite depth case, the new inclusion is very much an infinite index, yeah? Okay. Now, you should think of this if somehow the subfactor initially was coming from some group-like data, then this new inclusion will play the role of the cross product by this group. So it's really a cross product kind of inclusion that I want, I will stress later. Now, for the moment, we will only keep in mind very little about this inclusion. For the moment, we will do something extremely general. So the advantage is, if you were lost, if you don't know about subfactors or any other circumstance like that, we can start somehow from scratch now. Because we are now in a very general situation. This inclusion is a so-called quasi-regular inclusion. Of two unfactors. T in S is called quasi-regular. If S can be densely spanned finite index T subbimodules. Now that was by its very construction the case. By its very construction, I have spanned S by a sum of finite index T bimodules. Yes, so it was just by construction the case. Now what is, so example 1 is example 1, the ST impedance. Example 2. Is the case of cross products. So those who know cross product von Neumann algebras, where a group gamma is acting on another von Neumann algebra T, you build the cross product, and in that cross product, each TUG is a T bimodule, is a T subbimodule. So the usual conventions and the unitaries UG labeled by group elements are unitaries generating this cross product together with T. And then you have the usual commutation relations. So this is a T bimodule with dimension 1 from the left and dimension 1 from the right as well. Yeah? So very much finite index. Okay. Now the whole point is that there is a good way to look at representations and even L2 cohomology and cohomology for arbitrary quasi-regular inclusions. So that's the most general point of view. So that's what Sorin Shlyakhtenko and myself did at the end of 2015. So let me first define the representation. A unitary representation for T in S is nothing else than, by definition, is an S, a Hilbert S bimodule. A unitary representation is a Hilbert S bimodule such that H such that as a T bimodule, any S bimodule can be restricted to a T bimodule. We have a sum, a direct sum of T bimodules in a prescribed category C. In a given category of T bimodules C. Now, it's a very nice exercise to make. If you take a cross product inclusion, then there is a dictionary, one-to-one dictionary between unitary representations of this acting group gamma, and then all S bimodules, all bimodules for the cross product, which as a bimodule over T are a sum of these. Only these may appear as a T bimodule. Okay. Now, once you have, so this is just a definition, it's not very hard to come up with, and then you can start to write all kinds of things. You can say what is a positive definite function. That's the coefficient of the bimodule, if you wish. Positive definite function.
Stefan, so this means for this definition of unitary representation that you first specify a category C.
Yes.
So it's a definition relative to some
that it's relative to some category C of bimodules, although there is a canonical choice by just taking C, the one generated by the T bimodules appearing in S, because S is by definition of quasi-regularity, S is itself spanned by finite index T bimodules. And you could just take these and generate the category by these. That's what you would do in the group case.
Powers of S or just S?
Powers. In general, you would need to take powers, yes. Because it's not because S has a product. So indeed, it's tempting to say that if I have two T sub-bimodules, I can take their product in S. Now this product in S need not exhaust the complete tensor product as a T bimodule. So the main new things appear by taking tensor products rather than just a product inside S. Yeah. Okay. So what is now the language of a positive definite function? It is a completely positive map. Positive T-linear map. Phi from S to S, and so on and so forth. And doing this specifically for the symmetric enveloping inclusion, that's exactly Popa's original approach to defining Haagerup property, amenability, property T, whatever you may invent for a subfactor. You first go to the symmetric enveloping inclusion, where you apply these kind of concepts that were actually quite known already in the Van Neumann algebra setup. Now, of course, this is not a definition in terms of the standard invariant. I mean, it's a definition in terms of this larger inclusion. Now, the whole point is that I will explain you tomorrow why actually it can be intrinsically defined. So attached to this kind of structure, even for a general quasi-regular inclusion, attached to that comes an abstract algebra that would be the group algebra in the case of gamma. And we will show that having such bimodules is the same as having any star representation of this abstract algebra. And then in the category setting, this abstract algebra has a very nice description. It's the cube algebra. And then in certain cases you can compute it and you can link it to all kinds of things that happen in quantum groups. Yeah? Okay, so what's the plan? So let me try to wrap up by saying what is the plan. The plan is now that in lecture 2 I tell you how to attach to an abstract star algebra and this like C gamma and describe it and all kind of properties it has to related to representation theory. Then in lecture 3 do cohomology and algebraic numbers. Because as you may know, actually the whole story of algebraic numbers comes from the way the group algebra sits inside the group Van Neumann algebra. And here we will have the same thing. The star algebra will have a Van Neumann algebra completion. And then in lecture 4 I will give all kinds of examples and computations. Computations of Betty numbers, I mean. Okay, so that's the plan. Thank you very much.
Are there any more questions or comments?
The definition of positive definite functions in
the sense looks surprisingly simple.
Yes, so
Then the question is, I mean, is this correspondence, should I think of this correspondence as a GNS construction?
yeah, there is nothing in between these two.
Ah,
So
there's
No, these are just definitions.
So,
Okay.
so where's the, there's no category notion on the left.
No, okay, but I'm very happy that you asked the question, because maybe I have to say one more word about the symmetric enveloping case. So back to S being the symmetric enveloping algebra, where you now have a category of bimodules somewhere, and we had this, yeah? Okay, now what's so special about this one as a T bimodule? So T is M tensor M opposite. Now it's very much like in the cross product situation, because you see, by construction it's a sum of T bimodules, and each of these T bimodules appear with multiplicity 1. These are all distinct T bimodules, non-isomorphic T bimodules. Why? Because I restricted to the different irreducibles, yeah? So this means that what is a T linear map phi from S to S? Well, since each T bimodule appears only once and is irreducible, how can you define a T bimodular map on this? The only liberty you have is on each component you multiply with a scalar, because these are irreducible bimodules that all appear with multiplicity 1. So it's nothing else, it's just a map, say psi, on the irreducibles. Now the irreducibles, it's like the group, yeah, except that it's not a group. Now, what this whole formalism now allows is to single out which functions on the set of irreducibles of a tensor category are positive definite. Now, of course, it's in an extremely circumvented way, but what we will see is that it has a very nice intrinsic description as well. So you can say intrinsically in terms of the tensor category as well, which functions on the irreducibles are positive definite, or thus coefficients of representations. And then, for instance, the one formulation of amenability is that you can approximate the identity with finite rank, finitely supported positive definite functions, and everything goes through exactly in the same way. Yeah? Okay. Does that somehow?
So what then is completely positive? It's just that this number is positive real numbers.
No. You mean completely positive in the von Neumann algebra setting?
Yeah.
No. Completely positive as a map between von Neumann algebras means not only that it maps positive operators to positive operators, but that it still does if I do this on n by n matrices. So that's the good notion of a positive map between von Neumann algebras. For a functional, it would be the same to just say that you map a positive operator to a positive scalar, because that automatically inflates to matrices. But if it's from operators to operators, you have to tweak that it also should hold on matrices. For instance, from 2 by 2 matrices to 2 by 2 matrices, taking the transpose is not allowed.
But is there any GNS construction? Or?
Yes, sure. So the GNS construction to pass between these two is immediate. So when you take a T bimodule, then you would take, if you take an S bimodule, and then I would need a T central vector, and that will induce you such a map, and vice versa, there is GNS. Yeah.
Any more questions?
So I have a question about these two examples. So you inserted these two examples like particular cases of this more general setting, right?
Yes.
And this more general setting depends on the category, and there is a kind of natural category associated when you consider all these
Yes.
particular examples. But does it mean that even in these particular cases I can consider a different category and give something, or
You could.
I'm stuck with this canonical?
You could, but the point is that in both cases you somehow have reached the, not the maximal interesting one, but almost. So usually there are many different types of categories you could take, but giving rise to more or less the same structure. So in terms of the algebra that I want to define tomorrow, any choice you would make would lead to Morita equivalent algebra. So the representation theory would not change too much.
So it will show even that these canonical things are like really canonical.
You mean this example?
Natural
Oh yes, yeah, absolutely. Yeah. Now, for instance, the little nuance would be, you can already see it here. So that's the only reason why I gave it in that generality. The little nuance is the following. Look at this as M tensor M opposite bimodules, and start to tensor them as M tensor M opposite bimodules. It's not so clear that you can produce all H alpha tensor H beta bar. In general, you may not be able to do that by iterating tensor products. And then here, the natural underlying category would be the one where you allow all H alpha tensor H beta, for instance. But each time it just comes with one that's imposed. You should So I promise it will be much more down to earth and slow in the other 4 lectures here, because here I didn't know very well how to bring the whole picture at once. But anyway.
Any more comments? Or if not, thank you. So we'll meet again.